That'll give us, this is a leaving group, rather than Cl minus. First off, this isn't terribly, this is a fairly good leaving group. Maybe not as good as chlorine, but it's a sulfur oxygen minus that's in resonance with another carbonyl. So we've got this kind of like carboxylate resonance to stabilize it, plus it's on a sulfur, not a carbon, so that will give it maybe a little bit more. But the thing that drives this reaction is this isn't very stable. This isn't stable at all. This does what might almost be reminiscent of an E2 type elimination, where these more resonant electrons on this oxygen kick into the sulfur, kicking off Cl minus. They give us SO2, which is going to bubble away and give us Chatelier's on our side. So they'll give us SO2 plus Cl minus, which will just pick up this proton and give us our acid chloride plus HCl and SO2. But the reason we're able to get this to work is because we're bubbling up SO2. I saw someone tentatively reaching out to ask a question, or, all right. So that's pretty much what happens. This is the same mechanism as the book, I believe. But a key to think of this is carbonyl attacks SO2 to actually activate the system for attack by the Cl minus. And then it's just a tetrahedral intermediate where we have two good leaving groups. Just this good leaving group can collapse to give us a gas that bubbles away and invokes Le Chatelier's theorem to push the equilibrium towards the acid chloride. So that's how we make acid chlorides. So, acid chlorides are really a linchpin in nucleophilic acid substitution. If you need to do a nucleophilic acid substitution, probably the easiest thing to do is do a thionyl chloride reaction to transform a carboxylic acid, which you make through whatever way possible, in Jones oxidation under wet conditions, make a carboxylic acid. Then you can make the acid chloride just using thionyl chloride, DCM, and then you can do a nucleophilic acid substitution and anything you want into it. So acid chlorides are really a linchpin, or at least were a linchpin, until modern synthesis has come along, which we're going to really talk about for the rest of the chapter. But first off, I just want to talk about some of the other acid chloride things. So we know from an acid chloride, any nucleophile will add into it and it will happen. We know in hydrides, we make an anhydride, only anhydride's pretty much anything can add into an anhydride except Cl minus. So you can't make an acid chloride from an anhydride, but you can make anything else. All right? And so let's take our measures in anhydrides. And how would we make an anhydride? If I asked you to make an anhydride right now, what would you do? What would you start with? Yeah, exactly. So the most general way to make an anhydride, and I've done this a couple of times now, is to start off and make an acid chloride and throw in a carboxylate. In very select cases, particularly when we want to form a cyclic anhydride. You can make them one other way. So 95% of the time, you make your anhydrides through something along these lines. If you want to make a cyclic anhydride, you can if you will, go medieval. And in my notes, I think I actually have the hammer of Thor on my PowerPoint notes to really explain how this chemistry goes. So if you want to make an intramolecular anhydride, or you want to make a cyclic anhydride, what you can actually do is take a carboxylic acid, where the carboxylic acids are right adjacent to each other. So they have to be adjacent like this. So pretty much, in order for this to work, you have to form a 5-membered cyclic anhydride. However, 5-membered cyclic anhydrides are all over the place in chemistry, so it's somewhat useful. But if you can take your dicarboxylic acid, where carboxylic acids are right next to each other, heat this to like 300 degrees Celsius. That's really hot. That's really hot. And you'll get your anhydride out, plus H2O. Of course, this shouldn't be a reaction that's favored by equilibrium, right? We're going, pKa is 16, 16 versus, pKa of 4. Well, I guess it's an anhydride, right? So it's acid versus acid. But this shouldn't be you wouldn't think this would be a very thermodynamically favored reaction, because if this gives us this plus water, we know esters. We know we can form esters from anhydrides by adding water or an alcohol into an anhydride, and we're forming water. So we're giving up a stronger nucleophile, but the equilibrium favors this. So why does this not go backwards? So why does water not attack this at 300 degrees? Exactly. The Chatelier's theorem to the rescue again. At 300 degrees, any water we form is just going to fly off. And also, kicking off. Oh wait, the mechanism this goes through. Kicks up OH minus. Well, let's try the tetraketyl intermediate and ask ourselves what happens. So here's a tetraketyl intermediate of this. And this is going to kick down. And which one of these do you think would normally be the better leaving group? Oh, should be a hydrogen here. Right? So this would be the better leaving group. But do you think this tetraketyl intermediate is set up for a proton transfer? Yeah, absolutely, right? You can imagine. Well, first this O minus can take the proton. But what I always like to do? It's always much more satisfying when we have water to leave as a leaving group, right? So let's just let's just realize we're in equilibrium, and this will probably take the proton first. But eventually, through a productive pathway, this proton will find its way. Yeah, that was right. This proton will find its way to this oxygen. And we can kick off water to give us our anhydride. And the water won't stick around, it will evaporate. So we don't have to worry about the water attacking our anhydride and giving us our starting material again. So again, another way to overcome this idea of kicking off a stronger nucleophile is if the stronger nucleophile bubbles away or is boiled off, then it can't open up the stronger electrophile we made. So this is just attacking proton transfer, kicking off water, water boiling away to give us our anhydride. But again, this is medieval chemistry. I'm not making a pun. I'm not saying people in the medieval times did this, but this is harsh, right? 300 degrees, really hot. 300 degrees Celsius. Not like what you cook a pizza in your oven at home, Fahrenheit. This is like 300 degrees Celsius. Really aggressive conditions. All right, so best way to make to make anhydrides, but if you have to make a cyclic anhydride, this is the classic way to do it. Yeah.
The fact that water can boil off stops the oxygen with a negative on the second page.
Oh no, so all this stuff this is all in equilibrium, okay? And so the fact that water boiling up, what happens is, if water does not boil up, the water we form in this reaction would just attack this and give us our starting materials back. So water entered into equilibrium and would cause the reaction to actually favor the starting material. But since we're heating it so hot, the water is actually boiled away before it has a chance to cause the equilibrium to occur and cause it to go back.
But I'm asking, why doesn't the oxygen negative attack the...
Oh, why isn't this O minus? Oh, sorry, I mentioned that in passing, I didn't draw it up. It will take the proton first, but in these mechanisms we're interested in the productive pathway. So I said this will probably take the proton first, but eventually we'll find it so that this grabs the water and we kick up H2O. Yeah, but if you wanted to have this proton and kick up OH minus and have the OH minus leaving, take that proton as it leaves, you could. But I just like having H2O leaving myself. But yeah, no, and as I said in lecture, you definitely this would be the more basic oxygen that you would expect to take the proton, but we were just, we wanted the productive pathway. So anhydrides are great. Anhydrides are amazing, but and from anhydrides we can make esters if we add an alcohol, and we can make amines. And we can make amines. Or we can make amides by adding amines. So now let's talk about esters. So we know we can make esters either from the acid chloride, and this is a retrosynthesis arrow, or the anhydride. And this makes perfect sense pKa-wise, right? If you add methanol, methanol is a stronger nucleophile than Cl or carboxylate, so the equilibrium would favor the ester. So that makes sense. But what this would require us to do is take the carboxylic acid, make these, and then add our methanol. That's 2 steps. Making this, 1 step, and then adding the methanol to get the ester, 2 steps. Chemists are lazy. 2 steps is kind of a bummer. That's a whole 4 or 5 hours, then purification, and another 4 or 5 hours. What if I want to write now? Well, in theory, what would happen if we took a carboxylic acid and threw in methanol? This nucleophilic acyl substitution, substituting a water with an alcohol. Where would this equilibrium lie? Or would it lie anywhere? Or would it be equal?
Equal.
Based on the pKa argument, water and alcohol have similar pKa's, so there would be very, very little preference for either one pKa rise. And so, maybe we get some kind of slow methanolysis of this alcohol. But it's not going to be fast and it's not going to be good. So how do we get around this? Well, it turns out if you add H3O, then the reaction is supercharged, and that will really favor getting the methanol out. But the key is, under water conditions, we have to use methanol as our solvent. So if you use methanol as our solvent in H3O, we will get this as our major product. Why do we have to use methanol as our solvent under acidic conditions? French guy's name. Le Chatelier's theorem, right? By Le Chatelier's theorem, if you have 1,000,000 times access or 1,000,000 times access or more of one of the reaction partners, the equilibrium is going to shift away from that. And so under acidic conditions, if you use methanol as your solvent, you're going to get the ester. Has anyone done this reaction? Has anyone done this reaction? I know all of you who have taken the lab have done this reaction. This is a Fischer esterification. Fischer esterification. And so I know your lab TAs probably did a phenomenal job of explaining it, right? So